There I am. Welcome, everybody. We're going to talk about the average atomic mass. Now, this is one of the trends that the periodic table has, and we're going to actually, if that's over here, pen color, let's go with blue. All right, there we go. So what we mean by average atomic mass is one of the trends that we have on the periodic table, and it increases from left to right. So as we go from, say, lithium on the left all the way to fluorine on the right, it increases. It gets heavier, heavier, and heavier. And it increases from top to bottom. So as it goes down, lithium and down to francium, it's going to steadily increase. Now I want to point out that, look, if you look at some of the averages, they're not quite in order. Basically because some of the elements are not in order because of nuclear stability. For example, argon-39 is radioactive, and potassium-40 is radioactive. And they actually switch. So argon-40 and potassium-39 are stable. So argon is first, and has less protons than potassium, but its actually average atomic mass is actually a little bit heavier. So there are those little kind of idiosyncrasies. But honestly, folks, this is what we're using the periodic table for. If we know what the elements are, we can tell which one's heavier, which one's not. But on the periodic table, it is not a whole number. We actually is the average, and what the periodic table has what they call the average atomic mass. And we're going to actually show you how to calculate that atomic mass. And of it is basically we have the sum of each isotope times its relative abundance, and you add all those up together. The relative abundance should equal, or percent, should equal 100, or I'm going to say 1.00. But the thing is that the isotope mass is not a whole number. And I want to point this out because mass number, as we've been talking about, the mass of the isotope, mass number, which is protons plus neutrons, is a whole number. But when we actually determine the mass of a proton and mass of a neutron, it's not exactly 1. It's a little bit above 1. And so now the isotope mass, the actual mass, and I'm going to say this is the actual mass, is not a whole number. It is a decimal, a number plus a decimal. And now we got an idea of what we have to do. When we add everything together, it should equal 100%, or 1. If it's pretty close, 99.98 to 100.02%, you're fine. And I want to point out we're looking for relative abundance, not percent. So relative abundance, sorry about that. That is a decimal, and percent abundance is when you multiply this by 100%. There we go. So there's a difference between the two. Guess what? You did a lab on this a week and a half ago. So this should be relatively in your head. So on this assignment that we're going to work on, we're going to do this. We're going to calculate the average atomic masses of all these elements. And what I want you to do is create a table. And this is boron. And the boron has 2 isotopes, boron 10 and boron 11. Now if you look at boron 10, it's 10.012937. That's the actual mass of that isotope. And it has a relative abundance of 19.9. And then boron 11 has a mass of 11.009305. That's a long one. And a percent abundance of 80.1. First thing you do is this percent abundance, convert it to relative, 0.199 and 0.801, because you want the decimal. Then what we're going to do is we're going to take each isotope, multiply the isotope mass by the abundance, relative abundance. So I'm going to take this and multiply by 0.19. So 10.012937 times 0.199. And for boron 10, I'm going to get a value of 1.99257. 4, and let's see, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So end of the sixth decimal. Let's go ahead and carry this out to the sixth decimal place. I am trying not to touch mine. It doesn't like something I'm doing, so sorry about that. So boron 11, that's 11.09. So, excuse me, 2 zeros and 9305. And we're multiplying that by 0.801. And we're going to get 8.818453. And this is boron 11. So now we're going to add these two together. So that's going to be 7. 7 plus 5 is 12. Carry the 1. 5, 6, that's 10. 8 plus 2 is 10. Then I carry the 1, 11. We'll carry another one. 9, 10, 11. That's 18. So 8, 1. So that's going to be 10.811027. So this is the average atomic mass of boron. This number. So this is what we want you to get. All right. Now, in this case, we have 3. We're looking at potassium. Has three isotopes. One has 93.3% abundance. This is the most stable one. Potassium 40 is radioactive. Is very small. And then here's potassium 41. A little bit more than, definitely a lot more than potassium 40, but not as much as potassium 39. So we do create a table. Change this to relative abundance. Always change the percent to a relative, because honestly, all our tables have, whoops, I think I'm messed up here. It's easy to do, especially when you do it in your head. All right, so 0.0117 divided by 100. 1, 2, 3, then 117. That's better than 0.067302. So those are the not percent abundances, relative abundances of these 3 elements. Now we're going to take this and multiply by 0.93. So 38.9637007 times 0.932581. So it's going to be 36.336813. It's actually 28, so I round up to 3. So 39.963999 times 0.0117. That's going to be 0. And you got to do each one, guys. 757 9, and then 40.961826 times 0.067302, and we got 2.756813. And this is going to be a point of counting out to this, the 6th decimal place, because in the next chapter we're going to show you how to figure out mass defects, and we need this because this is how accurate we can measure, and this is how much energy that we're going to convert using mass equals mc squared. Einstein actually has something good there. So 2.756813 plus 0.467579 plus 36.336813, and we should have close to 39. We do 39.561205, and that is the average atomic mass of potassium. And that is the end of my lecture.